All right, today we're talking about the Doppler effect. The Doppler effect is the effect that you get when you have something that's making sound or making a wave and something that's observing a wave, and they're moving with respect to the medium that carries the wave. For example, when a car drives by honking its horn, what do you hear? Right? The reason that the pitch you hear changes isn't because the frequency that the car's horn is oscillating at is changing. It has to do with the motion of the car. All right, just to cut to the chase, the equation your book gives you to calculate Doppler shifts is this one right here. And let's just explain each of the terms. This over here, F, is the frequency that the source is oscillating at. So if this is a car horn, this is the vibration of the car horn. Or maybe it's a speaker that's moving. This is the frequency at which the speaker moves up and down. Or a guitar string moving up and down. All right? So that's the frequency that the source is oscillating at. F prime is the frequency that the observer hears, which can be shifted because things are moving. In this equation here, V is the velocity of sound. So there's a V on the top and there's a V in the denominator. Those are both the velocity of sound. All right? For standard temperature and pressure, the velocity of sound in air is 343 meters per second. All right? This velocity right here, V sub O, is the velocity of the observer relative to the medium. And this one down here is the velocity of the source relative to the medium. All right, so notice that I said relative to the medium. If you're doing Doppler shifts on a windy day, if the wind's blowing fast enough, it may make a difference. You would need to measure the velocity of the observer and the source, not relative to the ground, but to the wind. Measure them in a reference frame in which the air is at rest. Now, the air has to be moving pretty fast for this to be significant, but just I should point out that this equation works in the reference frame where the medium is at rest. All right? Now, what about these plus minus signs? Well, this upper plus minus sign is related to the observer, and the lower one is related to the source. All right? If the observer is moving in a direction towards the source, you use the upper sign. If they're moving away from the source, you use the lower sign. Down here in the denominator, if the source is moving towards the observer, you use the upper sign. If it's moving away from the observer, you use the lower sign. So, for example, if the observer is running towards the source, but the source is running away, all right? So somebody's honking their horn, you're following in a car behind them, all right? The observer is moving in the direction of the source, so you would use the upper sign in the numerator. The source is moving away from the observer, therefore you would use the lower sign in the denominator, all right? If they're both moving towards each other, so here's the source moving this way, here's the observer moving this way. The observer is moving towards the source, so you'll use the upper sign in the numerator. The source is moving towards the observer, so you'll also use the upper sign in the denominator. All right? If you ever forget, just remember that this sign has to do with this velocity, and this sign here has to do with this velocity. All right? So, which one is it? Is it plus or minus? Well, if the observer is moving towards the source, that's going to make the frequency go up. If the source is moving towards the observer, that's going to make the frequency go up, right? So if the observer is moving towards the source, we need a plus sign to make the frequency go up. If the source is moving towards the observer, down here we need a minus sign, because a minus sign in the denominator will make the observed frequency go up. All right? So there's the equation. Where does it come from? I mean, you can take this, you can plug numbers into it, work homework problems and what have you. But to understand, if we understand where it comes from, we'll understand it much better, we'll use it better, we'll know when it can be applied, and so forth. All right, but before we talk about where it comes from, if you want to see the effect for a moving source, here's a link you can go to on YouTube, and you can watch a video. It's basically just a car driving by honking its horn. You've probably heard this before. All right? But here's the basic idea of what happens. So imagine our car is driving by, and it's emitting sound waves periodically. But because the car is moving, it emits a wavefront here, and it emits a wavefront here. These ones are going out circularly. By the time we emit this one, the car has moved. So with time, it's like, imagine I have a lake, and I'm dropping pennies in the lake, and those pennies are making rings going out, right? But if I'm moving while I'm dropping the pennies, right, I drop a penny here, and this ring starts to grow out, but I drop the next penny right here, right, and so this ring right here is centered about, so each time I drop a penny, I'm going to make a ring. So the reason I get something that looks like this is I've dropped a penny right here, and I've got this wave just starting to come out, but this wave front that came from when I dropped a penny a while ago, I dropped it in a different position. Does that make sense? So if we're an observer here listening to these waves, this is my ear, listening to these wave fronts come, all right? The frequency that I hear is just going to be the speed of the waves over the wavelength, right? But what is the wavelength? The wavelength, right, you would think, so this is the frequency that I hear, I'll put a prime here, it is the velocity over the wavelength, but what's the wavelength? You would think, well, I've got something oscillating at some frequency, so this ought to be true, right, which means that the wavelength then is just velocity over the frequency making the wave. That's not true. Why is it not true? Because I drop in my penny, and my wave starts to propagate out, but by the time I drop the next penny, I've moved a little bit, all right? So if I was sitting still, right, so I drop a penny here, and I get this ripple, and it comes out here. When I drop the next penny and start this ripple, I've moved. So if I wasn't moving, the distance between the ripples, the wavelengths, would be this, all right? But because I've moved, the wavelength is actually going to be shorter. How much shorter? So let's call this lambda prime. We'll let lambda be what the wavelength would be normally. How's that? So we'll say lambda is velocity over the frequency of the thing oscillating, but I don't get that full wavelength because I've moved an amount, right? So lambda prime is going to be lambda minus that distance right there. And what's that distance? It's velocity times time, and the time is 1 period, right? Or, plugging this in for lambda, we have v over f minus v, I gotta be careful, this is the velocity of sound. I'm traveling at a velocity v source, right? There we go. So v source, and t is just 1 over f. So there we go. So lambda prime is just going to be 1 over f times v minus v source, right? So if I plug that in up here, I'm going to have a v divided by this thing. So when I divide by that, it's going to be f v over v minus v source. So there is the equation for a moving source. Notice it looks like the equation we had before here. If we set the velocity of the observer to 0 and we choose the upper sign. Why do we choose the upper sign? Because I assumed the observer is here, the source is moving towards the observer. The wavelength gets shorter, the frequency goes up. If instead we put the observer over here such that the source is moving away, then the wavelength would actually get bigger by that amount, and we would have a plus sign instead of a minus sign. All right? So there you go. That is the Doppler shift for a moving source. And that's exactly what our equation up here said it should be if the observer is not moving. But what if the observer is moving? Well, you can hear what happens by going to YouTube here. It's a similar video, only this time, instead of having a car drive by, Now the observer with the camera is in a car, and they pass another car which is sitting still and honking. All right? Sounds pretty much the same. All right, so if the source is sitting still but the observer is moving, you can see as I move across here, the wavelength isn't shifted. The wavelength is the same as if, well, the source isn't moving, it's just making some regular wavelength. But what happens, I've got these wavefronts, and they're spaced just as they should be, nothing's moving, but now if the observer is moving towards the source, right, the waves are moving this way, and how long do we have to wait between hitting wavefronts? If we're sitting still, the time is just 1 over the frequency, right? But if we're moving into the wave, we'll get a shifted period, right? It's going to be shorter. It's going to take less time, right? You can kind of think of it this way. I have some wavelength that's moving, all right? And the wavelength is moving at some velocity v, so the time that it takes for one wavefront to pass if you're sitting still is just lambda divided by v, right? But if you're moving into the wave, it's as if in your reference frame the waves are moving a little faster, right? So they're not just moving at the speed of sound, they're moving at the speed of the observer as well, right? And so f prime is just 1 over this. It's going to be v plus v naught over lambda. But v over lambda is just the undoppler shifted frequency, right? Yeah? So this is going to simply be, yeah, let's actually write this out. So lambda, we don't want to get rid of lambda. Lambda is just v over f, right? So let's write that out. V plus v naught divided by v over f, right? And so, yeah, there it is actually. Let's just circle that and we'll say that's what you get if the observer is moving. And that's exactly what we saw up here, the equation from the book. If the source is not moving but the observer is, it's just v plus v naught times f, right? V plus v observer times f. Now, if we were moving in the other direction, instead of taking less time for them to pass, we would have longer time, right? So there's our other sign if we're moving the other direction. All right? Now, how do we combine them together? Well, what we do is we say, well, if the source is moving, so if the source was moving, we had f prime is equal to f v over v minus plus v source, right? So this, first we say the source is, because the source is moving, the wavelengths in the medium are changed. And then we said if the observer is moving, we had this, right? F v plus minus v observer over v. Well, what we're going to do is we're going to say, well, look, the frequency's already messed up because the source is moving. It changes the wavelengths in the medium, all right? And then we're going to take this and plug that in as the frequency then that the observer is going to hear, only now the observer is moving, so it gets shifted again. And if we plug that in there, we get f prime is equal to f v over v minus plus v source times v plus minus v observer over v, and those cancel out. And we get the entire equation, which is good if the source is stationary, if the observer is stationary, if they're both stationary, if neither is stationary. And so that's where the equation comes from. All right? There it is. There's Doppler shifts. We already put it together. There it is. So remember, approaching, use the top sign. Moving away, use the bottom sign. I'm going to address a misconception that students sometimes have. Some students will look at the observer, so they'll, like, imagine, if you will, you're chasing a car. So here's a car, here's the observer, and here's the source. And let's say the observer is moving faster than the source. Some people would say, oh, they're getting close together, so that means use the top sign. I'll use the top sign here and in the denominator. That's wrong, all right? The top sign only has to do, the numerator only has to do with the observer, and the denominator only has to do with the source. So in this case, you would use the plus sign on the top and the minus sign on the bottom, because the observer, or sorry, and the plus sign on the bottom, because the observer is approaching the source, but the source is running from the observer. So when we have these two signs, right, this sign only has to do with what how the observer is moving in the medium. Doesn't matter what the source is doing. This sign here only depends on what the source is doing in the medium. Doesn't matter what the observer is doing. So if the observer is moving this way and the source is moving this way, it would be plus and plus. Doesn't matter who's going faster. All right? Okay. Now, the frequency is higher when things are approaching each other and lower when moving apart. So if you forget the signs, all you have to remember is I've got observer on the top and source on the bottom. And if the observer's approaching the source, well, I know the frequency has to go up, so that better be plus. If it's moving away, it better be minus. If the source is approaching the observer, the frequency should go up, but since I'm in the denominator, I make the frequency go up by putting a minus sign. If the source is moving away from the observer, that makes the frequency go down, which means I need a plus down here in the denominator. All right? Okay. Turns out light is also Doppler shifted, and that's really cool. You can use the Doppler shift of light to do some neat things. For example, if you look at the spectra, the atomic spectra of light coming from stars and galaxies, it's shifted to lower frequencies because they're moving away from us. Some are shifted more than others. That tells us they're moving away faster. You can determine how fast a galaxy or a star is moving relative to the Earth by measuring these Doppler shifts. An interesting thing happens. Long time ago, some people noticed that objects that were further away were shifted more to the red, shifted more to longer wavelengths. Therefore, they were moving faster. So the further things are away, the faster they tend to be moving. And that tells us that the universe is expanding. So we know the universe is expanding because of Doppler shifts. All right? Now, the Doppler shift for light is different than the Doppler shift for sound waves or waves in water. And that's because there's no medium for light, right? We talked about in that equation, we measure things relative to the medium. On a windy day, I measure the velocity of the observer and the source relative to the air in a reference frame that's moving such that the air is not moving in that reference frame, right? But it turns out with light, there is no special reference frame. There's no medium. Light just travels by itself, all right? And so you have to do some different physics. And without actually deriving the physics, here are the equations you get, all right? So instead of using the Doppler shift equation that we derived earlier, when you're dealing with light, this is the equation you use. Now, the variables have different meanings. F prime and F mean the same thing. But here, the speed of light is c, right? Before, the speed of the wave was v, but now we're calling it c. Just traditionally, the speed of light is c. And v represents the relative velocity of the source and the observer. So with the classical Doppler shifts like you have for sound, there is a separate v observer and v source, and they're two different effects, right? When we derived the equation for the Doppler shift, they were two separate effects. But for light, there's just one velocity, which is the relative velocity of the source to the observer or the observer to the source. So there's not two velocities. All that matters is, are they getting closer together or further apart? All right, if they're getting closer together, you use this equation. If they're moving further apart, you use this equation. So you look out at some galaxy, it's moving away from us. This is the equation you would use. You could measure the frequency that you measure. You know, though, that hydrogen emits some light at a certain frequency. So you can solve this and find the velocity that this galaxy is moving away from us. All right? Another way to do it is to always use this equation, but just decide in your mind that if things are moving apart, that represents a negative velocity. That's another way to think about it. All right? Now, why a different equation for light? Light is fundamentally different. As I said, light does not travel in a medium. Sound does not travel in deep space. It doesn't travel in a vacuum, but light does. Now, there's a lot of practical things you can do with Doppler shifts. For example, bats emit bursts of sound and listen for Doppler shifted reflections. So we all know that bats use echolocation to find things. A bat doesn't just know where something is, it knows how fast it's moving. It can predict where it's going by listening for the Doppler shifted frequencies. We do something similar with Doppler radar. We bounce radio waves off of clouds and things, and we can see how fast those clouds are moving by looking at the Doppler shift. When the police hit you with their radar gun, they're looking at a Doppler shifted frequency coming back. They shoot out radio waves, they bounce off of your car, and they're Doppler shifted because your car is moving. And as I mentioned, astronomers use Doppler shifts to determine how stars and galaxies are moving relative to the Earth. All right. Sonic booms. If an airplane moves faster than the speed of sound, you have some interesting things happen. If you would like to see a video of airplanes breaking the sound barrier, just go to this link right here. It's pretty cool. But imagine you got this plane going along, right? Imagine, so this is my plane. It's traveling along. Each of these dots represents a moment in time. So each of these circles was emitted, it's centered on one of these dots, right? This circle hasn't quite come out yet. This circle is a wavefront that was emitted when the plane was here. This circle right here was a wavefront emitted when the plane was here. This circle right here was emitted when the plane was here, and so forth, right? And so you can see the plane's going nearly the speed of sound. The wavelengths are very short here and very long here. So there's a very big Doppler shift as you hear the plane from this side and from here, right? But notice that this wavefront has gotten ahead of the plane a little bit, all right? So the plane is not quite traveling at the speed of sound. This is a plot of what happens when you're traveling at 0.9 times the speed of sound, or Mach 0.9. What if you're moving at exactly the speed of sound? Well, what happens is, right, this ring was emitted when the plane was here, this ring was emitted when the plane was here. Right now the plane's right there, and all of those rings, the plane is traveling at the same speed as the wavefronts are, and so they all pile up in front of the plane. All right, what happens if I go faster than the speed of sound, faster than Mach 1? Here's Mach 1.1. You see the plane is actually out in front of these wavefronts. All right? And if you look, there's an angle right here, and from that angle you can tell how fast the plane is going. So when a plane breaks the sound barrier, you can actually see this Mach cone. It'll actually make the moisture in the air turn into little clouds, all right? It becomes visible. And by measuring that angle, you can determine how fast the plane is going. And as I go faster and faster, that angle gets steeper and steeper. So right when I am right at the sound barrier, all right, the Mach cone is flat, and it gets sharper and sharper as I move faster and faster. All right, how fast is the plane going? What's the angle of the Mach cone? Well, here's how you could do this. We're going to take this point right here. We're going to connect the edges of these circles, all right? Let's just pick one circle, all right? So there's the center. So in some time t, we traveled some distance here, which is t times the velocity of the plane. Let's call it v sub p for the velocity of the plane, all right? This length right here that goes out and just touches the edge of this circle. What's the radius of the circle? The radius of the circle is the time. Let's use a tau. Let's use a t for time, because the capital T means period, right? So this length right here is going to be time times the velocity of sound, right? Which we'll just call v, all right? So now we can just do some trigonometry, right? I can say, well, this angle here, what's the angle here? We'll call this theta, call this gamma, right? And this is 90 degrees. We can just do some trigonometry because the hypotenuse is t times the velocity of the plane, and this side right here is the time from where the plane was when it emitted this wavefront and where it is now times the velocity of sound. So if we look at this, right, this just looks like a sine, right? Sine of theta is just going to be the time divided by the velocity of sound divided, or times the velocity of sound, divided by time times the velocity of the plane. And so then we can say, oh, if I know the sine of that angle right there, that's just equal to velocity of sound divided by the velocity of the plane. And as you can see, when the velocity of the plane is exactly the velocity of sound, that angle is, what do I take the sine of to get 1? 90 degrees, right? So that's when my wavefront is just a brick wall right there. And as the velocity of the plane gets really, really big, this angle gets shallower, and I get a sharper Mach cone. All right, here's an interesting thing. A Concorde pilot once talked about hearing a sonic boom. What is a sonic boom? Well, coming back up here again, you're sitting right here, right? You're happy. You haven't heard the plane yet. The plane has passed you overhead, but the sound waves haven't had time to get to you. You don't hear it yet. Then, so at some point, the plane's over here, and that boom hits you. All of these wavefronts are added together, and you hear it all at once. Boom! And then after it's passed, you continue to hear sound. So you hear nothing. Boom! You hear the sonic boom. All of this energy piled up in the edge of this cone, and then you hear the plane flying away. All right? Do you hear that sonic boom if you're in a plane? You don't actually hear anything on board. All we see is the pressure wave moving down the airplane. It gives an indication on the instruments, and that's what we see of Mach 1. But we don't hear the sonic boom or anything like that. That's rather like the wake of a ship that's behind us. And that's the end of our presentation.